In today's lecture, we will discuss about how to design a proportional controller, because in the previous lecture we discussed about how to design a on-off temperature controller, and we had used LM-336, that is IC sensor we had used for temperature sensing. Today we use thermocouple as a temperature sensor and then design a proportional controller instead of on-off temperature controller. So, so today's topic will be proportional temperature controller. So, we use thermocouple as a temperature sensor. Now, in this case we take second point is the heater voltage, because heater voltage as 100 volt is required. We will see for various heater voltage how to design, but first we take heater requires assume 100 volt DC, and then it needs assume say 5 ampere current, and then thermocouple will be used as a temperature sensor, will make a proportional temperature controller. Because if now if you see on-off temperature controller, there the controller was working basically, if temperature is low means, if temperature is low means lower than set temperature, then heater is on. If temperature is higher, that is higher than temperature set temperature is high, then heater is off. This is what we had seen, that is with high and low with respect to set temperature. For example, if I set 50 degree, if the temperature lower than 50, then heater is on. If the temperature is higher than 50, then heater is off. We also had shown there is a small region wherein you will have a hysteresis, that is on at one temperature, on off at to a different temperature, that we had seen in the previous class. But if we have this kind of on-off controller, essentially this is on-off controller. You cannot get very good temperature stability, because once it is on at, say, if I am setting at 50 degree, once the heater is on at 50 degree, then immediately it can't go. So, we had to give some hysteresis, that is if I switch on at 50 degree and then it will switch off only at 51 degree. Similarly, well, again it will come on only at 49 degree, and this is a must to avoid too much of on-off action, particularly if you are using a relay. Even if you are not using a relay, this will be going on-off, and even if there is no relay also, you will have this temperature hysteresis automatically coming from the system. So, if you want to have a high accuracy in temperature control, we have to go for proportional controller. In proportional controller, what we do is, in proportional controller, we will make such a way the error voltage, that heater voltage, actually heater voltage is proportional to the error. In the sense, whatever the heater voltage we are applying, that actually the error is here nothing but difference between set value, that is temperature is set temperature something and actual temperature something. So, heater voltage is always proportional to this. That is, if I set say 50 degree and actual temperature is 40 degree, then difference is 10 degree, then corresponding to that heater voltage will be there. Suppose difference is more, suppose if this is 50 and if this is 30 degree, then difference is more, now heater voltage will be more. If the error is more, heater voltage will be more. If the error is 0, heater voltage obviously will be 0. So, the heater voltage is no more on or off, it is actually the heater voltage will be somewhere between on and off. That is, if you have 100 volt as a heater voltage, depending upon the error you will have the heater voltage, it can be anywhere from 0 to 100 volt. So, the heater voltage basically proportional to the difference between the set temperature and the actual temperature. So, that is the basis of proportional controller. So, we have generate a heater voltage that is proportional to difference between set temperature and actual temperature. So, obviously, if you have to design, then I should have a actual temperature of the system should be known, and then what is the set temperature that should be known, and I have to find the difference. So, let us take the same example. In this case, assume that I have one oven here that I want to maintain this temperature. Then what I do is I will assume that I have here heater is there. Then I also put the sensor here. In the sensor in this case is thermocouple. I will show you how to make this thermocouple. So, you have the two ends are coming here. So, this is acting as a sensor, and then this is a heater voltage heater. Now, what I do is I take the sensor which is a thermocouple. So, thermocouple basically gives me if I take two junction thermocouple, then temperature difference between this junction say T1 and T2. So, you will get a voltage T1 minus T2 is the temperature difference between these two junctions into the sensitivity is the output voltage. So, most of the thermocouples if you see sensitivity is 40 microvolt per degree C, most of them will be in this range. Some of them you have 10 microvolt also there, some of them you have 59 millivolt for 59 microvolt is there, but we take average value which is around 40 microvolt per degree C. Most of the thermocouples give 40 microvolt. For example, chromal element thermocouple gives you 40 microvolt, because a thermocouple basically means two different metals gives you forms a junction, and the difference between the two junctions gives you the output voltage. So, for example, if this is at 100 degree C, if I keep this at 0 degree C, then the difference between this actually comes 100 degree C, then that gives me 40 microvolt into 100, that is equal to 4 millivolt will come from at these two ends. So, the temperature difference is high, you will get more voltage. That is how the thermocouple actually senses the temperature, and in fact, this is the only device that actually today gives you electrical output for a temperature. In fact, this is a good sensor not only to measure temperature, it can also be used to convert heat energy into electrical energy, because and in fact, this is the only device that you have for this. Only the basic device. Based on this one only, even other devices also generate electricity based on convert electricity, produce electricity from thermal energy. It is a very useful device. This has been extensively used in army to generate electricity, not only to measure temperature, but here we will concentrate more on how to use this to measure temperature, and in this case we use this to measure temperature and then also to control the temperature. So, what only one disadvantage in this thermocouple is we have to have, for example, if I want to measure the temperature, then I have to keep one junction at fixed temperature, say ice, then another temperature where I want to measure, say 100 degree C, then I will get the difference between these two junctions producing a electrical output. But then to keep this junction at a fixed temperature is a problem. So, in industry normally they do not prefer this 12 junction thermocouple, they use only one single junction. So, you have a single junction. So, basically we try to use single junction thermocouple. Other way around, actually it is only misnomer, there is no single junction thermocouple. The second junction is formed indirectly, like for example, if I terminate this single junction in copper, then this is one metal X, this is another metal Y wire. So, this X and this copper forming one junction here, Y and copper forming a second junction, and X and Y forming a third junction. So, basically you have one junction, two junction, three junctions are there. But then the end result of this is like this: if these two junctions 2 and 3 are at the same temperature, assume that it is a room temperature. So, I had put a big block in the room and terminated these two wires in this block with of course a small insulation here. So, insulation also essentially at the same temperature of this big block. Then the temperature producer is T1, and if this is say ambient, T ambient, then the voltage available between 2 and 3, voltage at 2 and 3 is actually T1 minus T ambient into sensitivity, where in this case S we have taken as 40 microvolt per degree C. So, for example, if invariably the ambient, say assume it is 25 degree C, and if this is say 100 degree C, then you will get 100 minus 25, it produces a voltage only for 75 degree difference, that is into 40 microvolt is sensitivity. So, that is 75 into 40 microvolt, that is microvolt. So, that comes, you will get 3 millivolt 3 millivolt as output voltage. So, it gives you corresponding to 75 degree only. So, of course, there is no issue because we have now eliminated one junction, and now we have to have only one junction, and then we have terminated in the room temperature. So, ice is no more required. But the problem is that if the ambient temperature changes, suppose if the room temperature changes, then you will have problem because we are terminated at room temperature. Suppose if the room temperature goes to 50 degree, then the same 100 degree at T1 will give you, for example, this temperature is continuously 100, but this had changed from 25 to 50 degree because the room temperature had changed. Then this will give you only 50 into 40 microvolt, that will be only 2 millivolt. The same 100 degree C now gives only 2 millivolt. Earlier when the room temperature was 25 degree C, the same 100 degree had given you 3 millivolt. So, if we are to be successful in using this, then we have to compensate this ambient temperature change, because when ambient temperature changes, the output generated by the thermocouple also changes actually. So, one have to provide ambient temperature compensation if you are using a single junction thermocouple. So, that we call generally it is called in industry circle ambient temperature compensation. So, what is done in this case is that you take the junction, keep it wherever the temperature to measure say T, and then the thermocouple is terminated in a block, isothermal block, say copper, with of course insulation so that it cannot get shorted. So, this is at T ambient. Then what you do is you measure this temperature using another sensor, say it can be like our IC sensor, which actually, for example, I give plus 15 volt here, then earlier we have discussed LM335. So, I can use for example LM336 can be used to measure the temperature of this block. If I know the temperature of this block, then there is no problem because I know T ambient, then I can find out from this output voltage what is the temperature of this. So, all that known is ambient temperature must be measured. So, use another sensor. So, if I measure the temperature of this block, that is ambient temperature, means the block is assumed to be in the ambient temperature, and we are measuring the temperature of this block. So, we have to measure the ambient temperature of this block, and then once you measure the ambient temperature of this, then you can find out the actual temperature by subtracting this. So, what is normally done is the measure the thermocouple voltage. Thermocouple voltage is actually nothing but T minus T ambient into S. So, that is voltage. So, voltage output. So, we know voltage output here and we know ambient temperature, we know since S. So, T can be calculated. This is how this is done. So, normally what is done is the output voltage divided by the sensitivity gives you the T minus T ambient, and T ambient is known. So, V0 by S plus ambient add, that gives me actual temperature of the junction, actual temperature to be measured. So, what is done is we measure ambient temperature separately, add with output voltage that is given by the thermocouple, of course considering the sensitivity, then you will get the actual temperature. So, this is what it is to be done. So, what normally done is you take the thermocouple single junction, you take, then take it and terminate it in a block, isothermal block, take it here. Of course, it is isolated, then normally you ground this, take the other point, other input, you get it amplified. For example, I have gain of say 24K, just for academic purpose I take gain of 25 here by putting 24K and 1K, then I will get at the output, because this sensitivity here is 40 microvolt per degree C. So, 1 degree change here will give me 40 microvolt change here, 40 microvolt change here, and 40 microvolt amplified by 25 will give me 1 millivolt. So, you will get 1 millivolt change for every 1 degree change at the output of this. But only thing is that the actual to know the actual temperature, we have to if you know the actual temperature, what we have to do is we have to measure this ambient temperature. So, I put one more sensor here in the same block. I will touch this mechanically I keep it, but there is no electrical contact to the block. So, I keep this one say plus 15, our LM336 335 sorry is a temperature sensor, not 336. LM335 is a temperature sensor. We know that at this point you will get temperature corresponding to this block. So, at 0 degree C it gives you 2.73 volt, 100 degree C it gives you 3.73 volt, which we had discussed earlier. So, this voltage must be suitably altered and added to this to get the actual temperature. So, we have to do that now, because this gives you 10 millivolt per degree C, whereas at this point you get only 1 millivolt per degree C. And the second problem is this is not giving at 0 degree C 0 volt, it gives you 2.73 volt if the temperature of this block is 0 degree C. So, normally what is done is we subtract out that 2.73. So, we can have this. So, we have V reference here, say 5 volt reference, if it is there I can have this arrangement to, so if this is plus, the subtraction it has to have minus. So, I add the minus voltage we had shown earlier how to decide on this R1, R2 and all. So, that I can get here 0 volt at 0 degree C, that can be achieved, and then at 1 degree C I will get 10 millivolt. This we had discussed earlier in our in the earlier discussion how to measure the temperature using LM335. So, I can do this and get output voltage corresponding to temperature here. Now, only thing is this gives me at this point 10 millivolt per degree C. Now, if the temperature goes up, that plus voltage is going up. So, if the plus voltage goes up, this will go minus, because more that temperature and you will get more the voltage. Of course, it will keep going in the minus side. For example, 100 degree C, I will get minus 1 volt. At 0 degree C, I will get 0 volt. At 25 degree C, I will get minus 250 millivolt. So that is good, because we of course we want to add this and this. So we can this and this is to be a same polarity, and then this 10 millivolt supposed to be made into 1 millivolt and to be added. Now there are two ways of doing this. I can also make it, for example, I can remove this plus 15 here. I put here minus 15, then I reverse this this chap, this LM335 only, but I reverse connected, so that now I will get minus 2.73 at 0 degree C. Then that minus 2.73 will come at 0 degree C. That will give me plus. So when temperature goes up, this will go up, more minus, that will make it more plus. So now what happens? Only thing is this is to be reversed. So I will make this as plus 5 volt. This and this will be opposite. So I put plus here and here I minus. So both are subtracting and become 0. So at 0 degree C it is minus 2.73. For example, I put plus 2.73, then I will get 0. When 100 degree C it will go to 3.73, minus 3.73, that will become plus 1 here, because this is kept only 2.73. So essentially, you will get now here 0 degree C you will get 0 volt, then at 25 degree C you will get 0.25 volt, at 100 degree C for example you will get 1 volt. That is what happens, that can be adjusted here. Now we have to add these two to get the temperature information. That we can do with one summing amplifier. So what I can do is I can take this, I can sum it up. Of course, this will reverse the thing, does not matter, we can reverse it again if you require. So I take this, then this voltage and this voltage are added up. So this gives me 1 millivolt per degree C, this gives me 10 millivolt per degree C, because the sensitivity is 10 millivolt and we are not scaled much, 1:1. So you will get 10 millivolt. So if I put all the ratios equal, then this will dominate, because we want to add ambient temperature with thermocouple junction temperature. That means if this is 1 millivolt, this also should be 1 millivolt per degree C, but this what we are getting is 10 millivolt. That is not difficult to solve. What we can do is we can scale this one. For example, if I have 100K here, I put 100K here, and I want this have a less contribution. So I can have 1 meg here, or I can have 10K, 10K and 100K here. So the ratio, now what will happen is that this and this are added. So you will have 1 millivolt change will come as 1 millivolt here. For example, at 1 degree C, this will give me 1 millivolt, and then if the ambient temperature is 25 degree C, then this will give me 0.25 volt. 0.25 will give me 25 millivolt at this point. Of course, this is plus, so this will come minus, and then this is also plus. So 1 millivolt will come as 1 millivolt here, that is also minus 1 millivolt. So I will get 26 millivolt here, minus 26 millivolt. Assume this is at room temperature 25 degree C, then I will get 0.25 volt here. That 0.25 will come as 25 millivolt here, because this is 10:1. So you will get 250 millivolt here, come as 25 millivolt here. Then if this is giving you 40 microvolt, then this will come as 1 millivolt, that 1 millivolt will come as 1 millivolt. So you will get 26 millivolt, representing the temperature is 26 degree, because if this is giving you 40 microvolt here, and if this is 25, if this is 25 degree, then only if this is at 26 degree, then difference is 1 degree, it would have given 40 microvolt. So that 26 degree junction temperature correctly appears at this output. So this is how the ambient temperature compensation is done, and you get at this point voltage corresponding to the temperature including the junction temperature. So the you will get at this point voltage corresponding to the temperature, and this ambient temperature compensation is a must, because nowadays in industry no one uses a dual junction thermocouple, everyone uses only single junction thermocouple. They always give ambient temperature as a compensation in this manner. So now what we have done is we have now got output voltage corresponding to temperature. Now this we have to use it for controlling the temperature. So now if I see this the whole circuit, that it looks like this. If I draw now, for example, I take this, then I put the block for terminate the junction, then I put the amplifier here to amplify the thermocouple voltage. Then we measure the temperature of this block by putting minus 15 volt. Then we take this, then we have put the ambient temperature compensation circuit. What we have done was that we go back and see our this thing. I retain the same circuit, that would be better. So I will put the another reference voltage, that is plus, and then same as what we had discussed earlier. And these two are added up. To get you the temperature. Of course, this is going minus side. If we want to make it plus, we can invert it, or even we can invert it, but I think we will not do that. We can simply invert it to get it such that you will get positive voltage. That would be easier for discussion, but nothing wrong in negative voltage. We can work with negative logic also, but for a beginner it confuses. So I made it such that the gain is here 1, and here you have R, and R we had a 10 R. So at this point you will get voltage corresponding to temperature. So that means at 0 degree C you will get 0 volt. If it is at 50 degree, then you will get 50 millivolt. So every 1 degree you will get 1 millivolt output. Now this should be used to control the temperature of the oven. So to control the temperature of the oven, what I have to do is I have to produce a error voltage. That is what the beginning of the lecture we have started. So we have to now get the error voltage. Error voltage means actual temperature that is given at this point minus the set temperature. So to control, then I have to have a set temperature and find the difference between this. So we can set the temperature by using a Zener voltage. For example, if I have a reference Zener here, say 5 volt Zener or 2.5 volt Zener available, I can have this, then say plus 15 volt available. I bias the Zener and put the potentiometer across the Zener. So across this, across this you will have 2.5 volt. So I use this potentiometer to derive whatever voltage that I need. So this is now acting as a set value, and this is acting as the actual temperature. So I have to find the difference between this and this. So that I can do it in different ways. For example, I can add a difference amplifier. So or I can even have summing amplifier if this polarity and this polarity are opposite. If this is plus and if I give here minus, then if I do the summing at the inverting input, then I will get minus. So I can do one thing. We know here I am getting already this is minus. So if I have plus here, I can sum it at this point. So probably what is done is you keep this one, for example, here. So if you see, say at 50 degree C, as we said, this gives me minus 50 millivolt. Suppose I want to stabilize the temperature at 50 degree, then I give here also say plus 50 millivolt. Assume this is also R. So, if I set this plus 50 millivolt and if the actual temperature also 50 degree, then this will give me minus 50 millivolt. So, this is plus minus and the ratios are equal. So, I will get 0 volt. There is a difference, that is the error will become 0, that is because our set value and the actual temperature are one and the same. So, if the temperature is 50 degree C, assume this is at 50 degree C. So, this is at say 50 degree C, then I know that I will get here minus 50 millivolt. Then if I want to say temperature to be raised to 100 degree C, assume that I put this junction in a oven whose temperature to be measured, then I want to keep the oven at 100 degree C. That means I will keep this junction in the oven and I want to take the oven to 100 degree C. Then what happens, if the oven is at 50 degree C, I know I will get minus 50. Then what I do is I will set this one to 100 millivolt. I will set this one to 100 millivolt. So, the oven is now at 50 degree C, so I will get minus 50, this is 100. So, the net result would be that you have a plus here more. So, you will get minus 50 millivolt here. You will get a minus 50. So, if I increase this as long as this is higher, then you will get more and more minus here. So, if the heater is on, assume that heater is on, then if this temperature goes up, then this minus also will go up. Then as more and more minus comes, this will also come down. When the temperature becomes 100 here, this will become minus 100 and this is plus 100, then this again will become 0. So, this obviously we are now what we have done is we have generated error voltage. Of course, the error is minus. So, we do not want normally minus logic. So, we can also make it plus logic by inverting it, that can be done. So, if we want, we can do that, or even we can invert previous stage and do that. I think we need not go back and we can simply invert it to get plus logic. So, I can have this. So, all that now comes is that I will get here if the temperature difference is 50, suppose if this is 100 and if the actual temperature is, suppose if the set temperature is, if the set temperature is 100 and the actual temperature is 50, then I will get plus 50 millivolt here. So, here you will get error 50 millivolt for example here. So, this point gives me error voltage. So, this voltage is nothing but T set minus T actual. Every 1 degree difference it gives you 1 millivolt. If the temperature, if this temperature is higher, output will be high. If this temperature is higher, output will be minus. So, so for example, morning when we come and switch on the oven will be at 25 degree C. So, this will be at 25 degree C, and if we had set 100 degree, say 100 millivolt here, then the difference is 75. So, you will get 75 millivolt at this point in the morning. So, this should obviously drive a heater, then only heater will heat up and go. So, what we do is this output what we have taken here, say I will name it as A, this output I should use it to drive the heater to complete the temperature control circuit. So, what I do is the next, I will take this output. So, I will draw from that stage, so that inverter stage what we have drawn at the end. So, that is coming from the previous stage. So, you have to previous stage what connected there, it goes there, and you will get here error voltage, that is this gives me T minus T ambient. For 1 millivolt per degree C is the sensitivity at this point, because every 1 millivolt difference will give me, every 1 degree C will give me 1 millivolt difference at this point. Now I have to proceed to the next stage, that is I have to, now I got a error voltage. Now I have to produce a heater voltage proportional to this error. So how will you do that? Now what I do is I amplify this to get the error voltage. So I can connect this and put a gain. Suppose if I give gains equal to 1000, then every 1 degree difference gives me 1 millivolt here. So every 1 degree difference will give me 1 volt at this point. Or even I can have say for example, if it is 10,000 gain, because normally we do not give in one single stage 10,000 gain. We will discuss about this more about this later. If you want, we can give 100 gain one stage, another 100 gain in another stage, that will make totally 10,000 gain. So at this point of time we assume that we are given 10,000 gain in one single stage, which is normally you should not do. You should give only lower gain only in any single stage. I will explain the reasons little later. So if we take this as 10,000 gain, then 1 degree difference will give me 1 millivolt here, and that will give me 10 volt at this point. This I should give it to the heater. We said heater is a 100 volt has to be driven. Now for example, I can give it to heater like this, and I want heater as 5 ampere current. So I put a Darlington pair, and then I give for example here 100 volt, and then I put the heater here. This heater is in the oven, and then there only the thermocouple is kept to measure that what we had seen in the previous figure. The thermocouple is actually physically kept here to sense the temperature of the oven. Now if 1 degree difference is there, you get 10 volt, and you will get if the 10 volt is present here, you will get 9.4 volt at this point, and then another 0.6 less here, that will give you 8 volt at this point. 8.8 volt will be applied to the heater. We always have to lose this 1.2 volt. But the problem is, we know that the output of the op-amp will not go beyond 15 volt, because if I am operating with 15 volt supply, I can expect only around 13.5 volt to 14 volt maximum, not more than that. So another 1.2 goes here, so you will get only around 13 volt. So but heater needs 100 volt. So with this arrangement, it is not possible to get 100 volt. If the heater supply requirement is less than 15 volt, then this works all right. So we will see first with this how it works, then we change over to 100 volt heater. We see how to make for 100 volt. So assume that this is only 15 volt and the heater needs only 15 volt. In that case, this circuit, this temperature controller works fine. Now if you see, if the set temperature is 100 degree C, and the morning if I come and switch on, and if it is at room temperature, that is at 25 degrees C is the set actual temperature. This is set temperature. 25 degrees C is the actual temperature. The difference is 75. I know that I will get 75 millivolt here, and 75 millivolt multiplied by 10,000 will give you 750 volt, and 750 volt cannot come. What is available is only 15, so 15 volt comes here, and here 13.8 comes and heater heats up, and then once heater heats up, then actual temperature will be keep rising, and this actually once actual temperature goes up, then voltage at this point will keep decreasing, because originally temperature difference was 75, so you got 75 millivolt. If the temperature difference is 10 degree, that is if the after some time the heater heater was after some time if the heater is on for some time, then the temperature of the oven goes up, and then the difference between the set temperature and actual temperature comes down. And if the set difference is only 10 degree, then this becomes 10 millivolt. Then 10 millivolt actually correspond to here 100 volt. But when the difference comes 1 degree, then it comes 10 volt. When the difference comes 0.5 degree here, then you will get 0.5 millivolt, and that will make this one to go 5 volt. That means now that means as the temperature, as the heater heats up, temperature is rising, and this voltage comes down, then this voltage also comes down. So it will be, if you give high gain, then for example in this case the our heater voltage cannot go more than 15, then once it comes to 1.5 millivolt, that is once the temperature reference is 1.5, this becomes 1.5 millivolt and this has come to 15. The temperature reference is less than 1.5 degree, then the difference will be less than 1.5 millivolt and this also will come out of saturation, that is also come below 15. That means this is operating in the linear region and this also will be operating in the linear region. So that means that means then heater will be, heater voltage is coming down. That means once the temperature rises, then at very close range, then this voltage will come down and this voltage also will come down and the heating also comes down. But at some point, you know, the whatever heat that is generated by the heater will be equal to heat that is going out. At that point it will stabilize. That is the idea of this proportional controller. So proportional controller to work, we have to make sure the gain is not very high, because if the gain is very high, it can easily become on-off controller. For example, if I put a gain of 1000, then for to get 15 volt you need 15 millivolt difference here, because 15 millivolt into 1000 will give me 15 volt. That means the heater will get into linear region, that is from fully on region it will start coming out and delivering less and less heat as this voltage rising up. But then with the gain is 1000, then if at 14 millivolt, that is at 14 degree away only, this becomes 14 volt. Then heating come down little bit. Then further if the temperature goes up, then this will come down to say 10 millivolt, then that is it come to close to 10 volt, then this comes to 10 volt. Now heating further come down, because now we are applying 10 volt minus 1.2, that is 8.8 only. Now if that heat is still higher to maintain this at 100 degree C, then this will still go up, this will come down because the temperature will go up and the difference will come down, and this will come to say 8 millivolt. If this difference comes to 8 millivolt, then this will go to 8 volt, then this also will come down. So as the temperature rises, this is coming down, you know, this voltage is coming down and the heater voltage also comes down and it produces less heat. So then the temperature rise at one point, what will happen, the heat coming here will be equal to heat going out, because as the temperature rises, the amount of heat, that is amount of voltage coming here and the amount of heat generated comes down, and net result is at one point the amount of heat going out will be equal to the amount of heat generated, and the controller will stabilize at that temperature. That means if you see very closely, if I set 100 degree, the set temperature is 100 degree. So if I take this, you know, the set temperature is 100 degree, then to maintain, assume that to maintain the oven at 100 degree C, the heater needs say 7 volt. The 7 volt here calls for 7 volt here calls for 8.2 volt here. 8.2 volt if you give only, I will get 7 volt. To get 8.2 volt, if the gain is 1000 here, if the gain is given 1000, then I need 8.2 millivolt here. That means 8.2 millivolt will become 8.2 volt and that will become 7 volt. Assume that 7 volt is what is required to keep the oven at 100 degree C. Then once it comes to 8.2 millivolt, this will become 7 volt, and then if the temperature is not going to rise anymore, and this will remain 8.2, this will remain 8.2, this remain 8.2, this will remain 8.2, and then this is at 7 volt. But mind you, you have a difference of 8.2 millivolt here. That means actual temperature is not 100, actual temperature will be 100 minus 8.2, that will be 91.8 degree only. That means if I set 100 degree C, then the oven will stabilize at 91.8 degree C, that will give a difference of 8.2 millivolt. That difference between this actual temperature and set temperature will be 8.2, that means actual temperature is 91.8, set temperature is 100, the difference is 8.2, that 8.2 will come here, that will come as 8.2 volt here because the gain is 1000 and you will get 7 volt here, and we assumed 7 volt is what is required to maintain around 100 degree C. So, this system will stop here, that means even though I had set 100 degree C, but system will not go to 100 degree C, it will stay away from 100 only, because if the error is 0, that is if the set temperature is equal to actual temperature, error becomes 0 and this becomes 0 and this becomes 0, no heating will take place, and without heating it can't keep the system at high temperature. So, you need always some heating voltage, that means always some error is required. That means if there is a error means the set temperature and actual temperature are different. So, proportional controller, this is one of the main drawback, that is if you want 100 degree C, then if you set 100 degree C, system not going to stabilize 100 degree C, it going to stabilize little less than 100 degree C, that difference only drives the heater, and this is one of the drawback of the proportional controller. Now, one way of solving this problem is that if I want 100 degree C, you set little more than 100 degree C, say you set 108 degree, then it will come and stabilize at 100 degree, that can be done, but then that the problem is not so simple. This error voltage what we have creates another issue in proportional controller, that is much more serious than what we have discussed so far. That is what we have discussed, the difference, that is error by itself is not a serious problem, the secondary effect of the error is the problem. So, the point that we should be noted at this point is in proportional controller, the set temperature is not equal to actual stabilized temperature. So, set temperature and the actual stabilized temperature are different. Set temperature is different from actual stabilized temperature. This difference only driving the heater. This difference only driving the heater. This is a very important point that we have to remember in proportional controller, and this difference produces secondary effect. This difference, this difference produces secondary effect. What is the secondary effect? And this is a very serious issue, because of this only we got PID temperature controller and so on, because if the proportional controller is much better than on off controller, because on off controller heater voltage switched on or off, whereas in proportional controller the heater is neither fully on nor fully off, it is in the linear range, but the error only drives the heater voltage. The net result is we are not getting what temperature that we wanted. If we want 100 degree C, then the oven going to stabilize little away from the set value of 100 degree C. Of course, you may say that I increase the gain, then the error will come down. For example, instead of 1000 gain, I put here 10,000 gain, then to get same 8.2 volt, I need only 0.8 millivolt here. For example, if the oven needs 7 volt to stabilize 100 degree C, then I need 8.2 volt here. To get 8.2 volt, I need only 0.82 millivolt if the gain is 10,000. So, I can increase the gain to make the oven go very close to the set value, But then if I increase the gain, then soon you will find that even very small difference makes this fellow to go high, and full 15 volts start coming here. That means it will become on off controller. So if we go for high gain, then system moves towards on off controller, and then you will find that similar to on off controller, the temperature also will be going up and down. So increasing the gain is not the solution to make the temperature to come close to the set value. Now okay, it is now, as I said, you know, the set value is not equal to actual where the temperature stabilize, then what is the secondary effect? The secondary effect is like this. See, the heater, now we assume that heater needs 7 volt. So I will explain with another figure what is the secondary effect. See, we have taken the, I draw only the heater part and the last part. So you have the heater voltage here, and the heater was driven through a Darlington pair, and the heater voltage was given to this, and you have here plus 15 volt, and then this is the final op-amp output that was given to this, and this is the gain stage. We assume that you have a gain of 1000. This is the V input come from the error voltage. So if I want, you know, here if I want the 8 volt, then I need, if the gain is 1000, I need 8 millivolt here. Now assume that the ambient temperature is 25 degrees C. This is where our thermocouple is kept, and we want to maintain this at 100 degrees C. So I had set 100 degrees C, the ambient is 25 degrees C is ambient. Now at when ambient is 25 degrees C, then the system comes 8 volt here, and then this fellow stabilizes at 91.2 degrees C only, because it can't go to, I had set 100 degrees C, but it does not go to 100 degrees C, it goes only 91.2 degrees C, because if you try to go more than 91.2, then this error will come down, then the heater voltage, you know, if this goes trying to go more than 91.2, this error will come down, and this voltage also will come down, and the heater will not able to maintain 91.5 degree if the voltage and the heater comes down. So now it has stabilized at 91.2, but we wanted 100 degrees C, and this is situation at 25 degrees C ambient. Suppose the ambient temperature goes up to 50 degrees C. See, the ambient temperature goes up to, temperature is 50 degrees C, if it goes 50 degrees C. Then then what will happen? The oven will radiate only less heat, because the oven is 100 degrees C, the ambient earlier it was 25, now it has gone to 50 degree. That means now less heat will come out from the oven, and then the temperature will try to go up. Then once temperature trying to go up, this voltage will come down, the error will come down, and this will also reduce. But then since the less heat only going out from the system, and it also needs only less heat only to the system, because heat going out should be equal to heat coming in, at that point only the system will stabilize. Since the ambient temperature has gone high and only less heat is going out, now this needs only less heat, that means now it does not require 8 volt, it needs, assume it needs only 4 volt. Assume this needs 4 volt, that means at this point it will come to 5.2. That means 5.2 means this will come to 4, and at 4 volt is enough to make that heat generated by this equal to heat going out. So what will happen is, to get 5.2, I need only 5 millivolt difference here. So I do not need 8 millivolts, I need only 5.2 millivolt. So now what happens, when ambient temperature gone to 50 degree, eventually what happens, this will come to 5.2 millivolt, this will become 5.2, and that 4 volt is enough to maintain this. So what will happen, this temperature will not be now 91.2, this temperature will be 94.8 degree. That means when the ambient temperature increased to 50 degree, this has gone to this 94.8 degree C. When the ambient temperature was 25 degree C, the oven was 91.2 degree, 91.8 degree C. That means we are not changing the setting of the temperature, we are kept on 100 degree setting. When the room temperature is 25 degree C, this is stabilized at 91.8 degree. When the room temperature went up to 50 degree C, it now went and stabilized at 94.8 degree C. It looks as if the oven temperature is changing with the ambient, even though we are not changing the setting. So it is like this, if I have a proportional controller, if I set this at 100 degree C and come and see in the morning, and morning room temperature is 25 degree C, you will see that the oven is stabilized at 91.8 degree C. Then I leave it, I do not change any setting, but then I will come in the noon when room temperature gone up say to 50 degree, then I will come and see at that time it would stabilize at 94.8 degree C. That means without doing anything, it looks as if the controller is stabilizing at different times at different temperature, even though temperature setting is not changed. This is happening because the heat coming in has to be heat going out, at that point only it stabilizes. Since heat going out is changing, correspondingly the amount of voltage that is required also changing, that amount of voltage generated by the error voltage, so the error voltage also changing. So this is one of the drawback of the proportional controller. So one have to be if the temperature have to be constant throughout the day, then only choice is you increase the gain, do not keep low gain, you go for high gain, but high gain will make it this temperature going up and down. If you keep at low temperature, then from morning to evening, if you watch the temperature of this, that will be changing slowly. So this is a serious problem, and this was recognized by the practicing engineers in the industry first, because after all this temperature controller and this theory controller all are actually generated not by the academic people, they are all generated by the practicing engineers who had done through trial and error method, generated the whole lot of theory for on off controller, proportional controller, PID controller and so on. The latter the academic people added too much of mathematics into that, and they also complicated I would say in a certain way. Actually the proportional controller, PID controller simpler things were invented by the practicing engineers for real world applications. So proportional controller is very good compared to on off temperature controller to get good stability, but then the set temperature, that is the actual temperature, continuously changes according to the ambient temperature. This is a serious drawback. So this issue was addressed by the practicing engineers, and then they developed the so called PID temperature controller, proportional integral differential temperature controller. In fact, the first step is proportional integral temperature controller. So they they added integral action to solve this problem, that is when ambient temperature changes, the temperature of the oven changing, that problem was solved by adding a integral action to this. So how that problem is solved, this we will see in our next lecture, because it is a very interesting topic how the PID controller evolved and how it is working. If one try to understand leaving the mathematics, it would be good. So I will try to explain everything without introducing any mathematics. It is better to understand that way before getting into mathematics. In fact, I am not going to touch the mathematics at all in this. Thank you.